Hey, welcome back. Today we're going to continue our study of arithmetic sequences and see what happens when we start adding them up. Remember, that's called an arithmetic series. To begin, I want to teach you about this guy. This guy is Carl Gauss. And Carl Gauss, as a little kid, was kind of like me, kind of really good at math and kind of really annoying to his teachers. And so one day his teacher needed to give him something to do to just stay busy. And so she asked, hey, what is the sum of the first 100 numbers? Figuring, hey, this is going to keep him going for a long time. 1, 2, 3, 4, and so forth. Add them all up. That would take a long time. But of course, he's like, oh, I know it, 50-50. And the teacher, I guess, got mad at him and threw a book at him and kicked him out of class, only later to find out that he was right. And so I wanted to show you how he found that answer, and that technique is a good strategy for us to use when we're adding up arithmetic sequences too. So how he did it was he imagined the numbers written forward like this, and then he imagined those same sequence of numbers written in reverse. And he added those two sequences together. If you add these up, then over here we've got two series. And each one of these totals is exactly 101. And so we've got two series of 101s. And how many 101s are there? Well, there are 100 of them. And that's a pretty easy multiplication to do. 101 times 100, that's just add two zeros, is 10,100. And because you have two of those, you divide that in half. And so he was able to do that in his head, which is pretty remarkable. But when you boil it down to that, I mean, it wasn't really that hard, was it? That technique is called the Gauss method of adding up an arithmetic sequence. I want to do it again, but this time I want to do it without actual numbers in it, but just a pretend sequence. One that starts off with A1, and then A2, and then goes until we have the nth number in the list. So let's imagine rewriting that in reverse and adding it up. So if we add those two things together, we have two series, and each one contains whatever the first number and the last number is. This is maybe 4 steps bigger, but this is 4 steps less, so it still adds up to the same thing, and so forth. So you've got a bunch of terms that all add up to the same thing as the first and the last. How many of these terms do we have? Well, if there are n items in this list originally, then there are n of these terms. And so we can rewrite this as saying that twice our sequence is n times the first and the last numbers. And therefore, if we want our series, our total, we can divide by 2. And this is a nice formula that you can use to add up the numbers in an arithmetic sequence. You take the number of numbers in your sequence, you add that up, or add the first and the last numbers together, multiply that, and divide by 2. By the way, this can sometimes be thought of as the average number times how many numbers you have, because the first and last numbers, add them up and divide by 2. That's the average times n. So now the question is, how can we find the sum of an arithmetic series? And there's a handful of different ways you can do that. So here's a couple of strategies you can think about. If it's a small enough sequence, maybe you can just write it out and add them up. But if you've got like 30, 40 terms in it, that's probably not a good technique. We can use the Gauss method. Write it forwards, write it backwards, add them both up, divide by 2. We could use sigma notation. You could check that other video if you wanted to know how to write something in sigma notation and use a calculator to do it. Or you can use a formula. The formula we just derived was this. Take the number of terms, divide it by 2, multiply it by the first and last terms. And there's a bunch of other formulas that you could look up. This one doesn't require the last number, but it does require the triangular number sequence. Here's one that doesn't require anything fancy except for the number of terms, the first number in the list, and the difference. And you could look up dozens more formulas online if you want, but by far the most popular one is this one from Gauss's technique. Here's an example. Let's find the sum of the first 60 terms in the arithmetic sequence that starts with 9, and then 14, and 19, and so on. So let's look at all of our different strategies. We could write it out. There's only 60 terms. it is COVID-19 season and there's nothing better to do. And so maybe you simply write out all these different terms and see what that gives you. Let's try it. So we've got 9, well, the first number, the second number, the third number, the fourth number, fifth number. And so we've got 9 plus 14 plus 19. And then what would be next? 24 and 29. And the sum so far is 9. After 2 terms, we've got 23. After 3 terms, 23. Oh, goodness, this is going to take forever. Nope, not going to do it. All right, let's try Gauss's technique. So Gauss's technique says to take this equation and then write it again underneath. And so to write it again underneath, we have 9. Oh, shoot. What's the last number in this list? Oh, I don't know the last number in this list. All right, maybe we can find it a second. Let's bring this back up again. So we want the 60th number in this list. Well, we could come up with a formula for the nth term. The nth term is the first number in the list, 9, plus the common difference, which looks like this sequence is going up by 5. And so then we could multiply by n minus 1. So if we want to know the 60th number in the list, we simply put a 60 in for n and see what it calculates out to. That was my calculator here. So 9 plus 5 times 60 minus 1, which is 59. That total ends up being 304. So now I know what the last number in the list is. Now I can use Gauss's formula. So let's pull out Gauss's formula here. Remember, 1/2 times the number of terms times the sum of the first and last terms. And if we fill in some of the numbers, we know there are 60 terms in this list. The first number in our list is 9, and we just figured out the last number in our list was 304. And so if we add those together, 9 plus 304 is 313, multiplied by 60 and divided by 2, we get a total of 9,390. So there's one way to answer our question. We used Gauss's method on it. This would be the same technique essentially as using a formula. And so I don't know that I need to do that again. But I do want to show you how we could find this using sigma notation. As a reminder, with sigma notation, we need a formula for the nth number in the list. And we found that just a moment ago. We said that that was 9 plus 5 times n minus 1. And then our variable this time was n. And we want to start with n equals 1. And we want to go 60 terms into the future. So we put a 60 up here. So if you wanted to type that into your calculator then, you would have to type a sequence of, and the formula is 9 plus 5 times n minus 1. Our variable is n. We're choosing to start at 1 and go until 60. If you typed this in the way I have it written with sequence in front, then what you will see is a list of numbers, 9, 14, 19, and so on. And you could scroll to that list and you would see the last number in the list is 304, which is kind of cool, but that's not what we really want. We want the total. So what we would need to do then is do sum of answer. Or you could do this all in one big step and type sum of sequence of and get your total that way. Some of the newer calculators have a summation symbol, a little sigma like this. And so if you have that, you can follow the little wizard that goes through there. It'll ask you for all the same sort of steps. It'll say formula, I think, variable, start, stop. It has one extra step, like, see what I did there? Step. I think it actually says step in there, or step size or something like that. That would be a 1. Because you want n to go up by 1s. So anyhow, that's a couple different ways that you can find a sum. Let's look at a different example. So in this example, we want to add up the terms in this arithmetic sequence, 5 plus 4.8 plus 4.6 and so on until we get down to 2. So our strategies, we could write it out. It doesn't look like there should be that many terms. It might be 20 or 30 terms in there total. So it's a doable option, but not very fun. We could try Gauss's technique on it. If we wanted to use Gauss's technique, we have to write it again in reverse. And so let's do that a moment. So here is our original sequence, and here is the new sequence. We can add this up, and so it is 7 plus 7 plus 7 plus, and so forth. And the last term would be another 2 plus 5 is another 7. So the key here is to figure out how many 7s there are. And unfortunately, I don't know exactly how many 7s there are. I would need to know what number in the list, what term in the list this final 2 is. And so to do that, I think I need to go on a little side quest a second and come up with a formula for the nth number in this list that I can then use to solve for 2. So if I want to create a formula for this sequence, that would be an is equal to the first number on the list, which is 5, plus the common difference, which is, it looks like we're subtracting 0.2 each time. In fact, I'm going to write that as a minus 0.2 times n minus 1. And what I really want to know is what n makes this equal a 2. And so why don't I make this a 2 here at the end, and we can solve this. So I would subtract 5 from both sides. That gives me negative 3 equals negative 0.2 over n minus 1. I think I'm going to divide both sides by negative 0.2 a moment. So negative 3 divided by negative 0.2 is 15. And that's what n minus 1 is. So if I add 1 to both sides, we get that n equals 16. And so what that ultimately means for our sequence here is that there are 16 7s in this list. And so 16 times 7, 16 times 7 is 112. But this was our list doubled. And so our total that we're interested in is half of 112. Half of 112 is 56. So there's our total. Kind of neat that we didn't really have to have a formula memorized to be able to answer this question, but it did require that we went on that little quest, if you will, to find that this was the 16th number in the list. It would have been nice to know that, and sometimes you don't always have all the information you need right away. One last question. This question says, how many terms are needed to reach at least 10,000? And so this is kind of asking the question in reverse. I don't have a list that I'm trying to find a total, but I want to know how many of them I need. So let's see what our different strategies are and if any of them would help. We could write it out, which would just involve like maybe on our calculators doing 1 and then plus 3 and then plus 5 and then plus 7 and just keep going until we reach 10,000. Normally that would be kind of a crazy strategy, but in this particular situation it might actually work, and let me show you why. So if I pull out a table here and start filling things in, the first 4 numbers in this sequence are a 1 and then a 3 and a 5 and a 7. And that would continue on with a 9 and 11. We've seen this sequence before, it's the odds. Let's start adding them up and just see what we get. So 1 plus 3 is 4, 1 plus 3 plus 5 is 9, 1 plus 3 plus 5 plus 7 is 16. We've seen this before too, I think. And it happens that this particular sequence, when we look at its series, is a very predictable pattern. The 5th partial sum, we say, is 25, and the 6th partial sum is 36, and the 7th is 49, and in general, the nth partial sum is simply n squared. And so if we wanted to know what n we need to get a total of 10,000, that would be the square root of 10,000, which happens to be exactly 100. And so normally I think writing it out would not be a good strategy, but in this particular case, because it happened to have a nice pattern, it worked. And so I want to make sure that you consider that strategy occasionally. But let's see, what if we were less smart and more mathematical and just tried to use a formula or something like that. Gauss's method is not going to be super easy here because I don't know what the last term is, nor do I know how many terms I need. So sigma notation, well, it could maybe work, especially if you use the cumulative sum on your calculator. You could kind of scroll through that list until you reach 10,000. I think I want to use a formula here. So here is a formula for the total. And this is Gauss's formula, right? 1/2 how many numbers, first and last number. And I want my total to be 10,000. And I want this to be at least that. And so I'm really solving an inequality here. Now, problem is I don't know what n is. I do know the first number in the list is 1. And I don't know the last number in the list. But we can write a formula for any number in the list that depends on n. And if I do that, then this inequality will just have one variable in it, n. And so let's take a moment and figure out what the nth number is in this list. So to do that, that is going to be the first number in the list plus the common difference, which is 2 times n minus 1. So here is a little bit of an unwieldy equation here, but we can clean this up a little bit. Let's distribute. That gives us 2n minus 2, and combine like terms with that 1 there. That would be 2n minus 2 plus 1 is minus 1. And then we can add this one into it, and that will give us 2n. And if we clean this up, the 2 and the 1/2 multiply together to give us 1 times n squared. And so we've got n squared, which shouldn't surprise us. That's what we had kind of figured out when we used the table and wrote it out by hand. And so now this is pretty easy inequality to solve. Simply take the square root of both sides, and n would be 100. So, anyway, there's a couple examples of how you can add up numbers in a series, an arithmetic series specifically, and a couple strategies you can use. Feel free to let me know if you have any questions, and I'd be glad to help. And catch me in the next video when we start looking at geometric sequences and series.